In this video, I'm going to look at extensive form game. And we're going to consider the solution concepts for the extensive form games. So first we'll look at the concept of sequential rationality. This is an assumption, and we assume that the players are behaving in a sequentially rational manner. And we're going to use this sequential rationality concept to analyze the extensive form game using the solution concept of the backward induction argument. So first, let's look at the sequential rationality. What do we mean by this? So an optimal strategy for a player should maximize his or her expected payoff, conditional on every information set at which this player has the move. Meaning that the player I's strategy should specify an optimal action from each of the player I's information sets, even those that player I does not believe ex ante will be reached in the game. So let's look at an extensive form game to understand the concept of sequential rationality. So here we have a game where we have two firms competing. So firm one is the incumbent firm here. So firm one is the incumbent firm, and firm one is the potential entrant. So let's write it down, potential entrant. And firm two is the incumbent firm. Okay, so this is a game of price war. So if firm one, the potential entrant, remains out, meaning it does not enter the industry and compete with firm two, then the payoffs are 0 to firm one, meaning firm one is breaking even, making normal profit, and 4 to the incumbent firm. In that case, it has monopoly. But if potential entrant, the firm one, if it decides to enter, meaning it's in, that's the strategy, then the incumbent, which is firm two here, has two actions at its decision node. Either it can accommodate firm one, in that case, they split the payoff 2 and 2, or it can initiate a price war. In that case, they both incur losses of $1. Okay, so this is the game here. So let's convert this game into a normal form game. So here you have the normal form game where it's a 2x2 game. Player one, the potential entrant, has two strategies in and out, and the incumbent, which is firm two, has two strategies: accommodate or initiate a price war, and the payoffs are given here. Right. So this game, normal form game, has been converted from the extensive form game, and we have discussed this conversion process in previous videos. So you might want to refer to those, how to convert an extensive form game into the normal form game. All right. So if we solve this normal form game using the concept of Nash equilibrium, you will realize that we have two pure strategy Nash equilibria in this game. So, player one will choose to move in if player two accommodates, right? That's the best response. And if player two, initiates a price war, then the best response for player one is to stay out. So this would be the best response. And similarly, if player 1 chooses to move in, then player 2's best response is to accommodate. And if player 1 chooses to stay out, then player 2's best response is there's a tie here. So both of these are best responses, right? So clearly the best responses match here and here, and they are the Nash equilibria of this game, right? So there are multiple Nash equilibria here. However, not both of them are sequentially rational. So let's look at that. So to sequential rationality, specifies that a player must choose his or her optimal action at any given information set, even if that information set is not reached, right? So let's look at player 2 first. So player 2, which is the incumbent, right? It has one decision node here, as you can see. So let's say player 1 moves in, competes with player 2, right? The firm 2 here. Will firm 2 initiate a price war? That is the question. Clearly, if you look at the payoffs, it is not in the best interest of firm 2 to initiate the price war, because that will result in a loss of $1. But if it tries to accommodate firm 1, then it makes a profit of $2. Clearly, profit of $2 is better than making a loss of $1. So if this decision node is reached for player 2, then the optimal strategy for player 2 is to accommodate firm 1, right? And similarly, firm 1 will, before making a move, whether to, stay out or move in, will anticipate what firm 2 is going to do. So firm 1, if it chooses to stay out, it makes a profit of $0. But if it moves in and player 2 behaves irrationally, right, at its decision node, then firm 1 can expect to receive a payoff of $2, right? So clearly 2 is better than 0. So the sequentially rational move for player 1 is to move in. So if you look at that, then clearly this Nash equilibria does not follow the sequentially rational path. However, this one follows, right? So this one follows the sequentially rational path, but this one, the Nash equilibria given by O and P is not, because player 1 will not, when it chooses out, that's not a sequentially rational strategy for player 1. So player 1 would not choose that. So as you can see, sequential rationality assumption allows us to remove one of the Nash equilibria from this game. So you can think of it as a refinement of Nash equilibrium concept. All right. So that's the idea behind sequential rationality. Next, let's look at the solution concept of backward induction argument. So backward induction argument is the process of analyzing. So let's look at it. So it's a process of analyzing a game from the end of the game to the beginning of the game. So basically you are moving from the last stage of the game to the first stage of the game. So at each decision node, one strikes from consideration any actions that are dominated. Given the terminal nodes that can be reached through the play of the actions identified at successor nodes. So backward induction implies that we go to the end of the game first. And from there, you look at any dominated strategies for the players and you strike them off from the game. And then you are going to move to the next stage, you're moving towards the first stage. So if there are several stages, let's say you have 4 stages in the game, so then you go to the 4th stage first, and you're going to identify which one are the dominated strategy. You strike them off. Then you move to the 3rd stage of the game, and whoever is playing the 3rd stage will look at, what are the strategies, what are the payoffs, and then you are basically going to delete the dominated strategies there. And then in this way, you're moving to the 2nd and the 1st stage of the game, right? So let's consider an extensive form game to analyze, So here we have, in this game, we have 2 players, player 1 and player 2. And here we have 3 stages of the game. So let me identify those for you. So player 1 plays the game at the initial node and has 2 strategies, up or down. And then player 2 gets to see what player 1 did in the 1st stage of the game. And player 2 has 2 decision nodes, upper node here, bottom node here, for every action of player 1. And player 2 has 2 strategies at every decision node. So it can move, A or B, or it can choose C or D, right, at the bottom node. So these are different strategies. And if player 2 chooses A or B, the game ends with payoffs of 1 and 4 and 5 and 2. And if player 2 at the bottom node chooses C, then the game progresses to the 3rd stage, where player 1 gets to play the game again. And player 1 can choose either E or F, right? And game ends. But if player 2 chooses D, then game ends with some payoffs. So I'll give you some payoffs here. So let's say it's 6 and 2, right? All right, so that completes this extensive form game here. So let's use the concept of backward induction argument to solve this game, right? So first we go to the last stage of the game. So the last stage of the game is the 3rd stage, where player 1 gets to play the game. So here, right? So the question is, if this node is reached, and that's conditional on player 2, getting to play at the bottom node and choosing C, right? It's all conditional on that. But let's suppose this node is reached. What would player 1 do? What is the optimal strategy? Would player 1 choose E or F, right? Clearly, if player 1 chooses E, player 1 ends up with a payoff of 3. And if it chooses F, it ends up with a payoff of 2. So 3 is better than 2, right? We're trying to maximize the expected payoff. So clearly, this strategy is suboptimal, right? It's dominated by E. And therefore, we can remove that, right? So if the game is reached the last stage here, the 3rd stage, then the outcome would be 3 for player 1, 3 for player 2, right? So we have solved at the last stage. Now, let's move backwards to the 2nd stage of the game. And there are 2 decision nodes at the 2nd stage, right, for player 2. So we have to specify what player would do at every decision node. So let's say the bottom node is reached. So what would player 2 do? We know player 2, if it chooses down, right, D, then is going to end up with a payoff of 2. And if it chooses C, then the game progresses to 3rd stage, where we're assuming player 1 is going to behave rationally, right? It's a sequential rationality assumption. So player 1, we know, is going to end up choosing E, right? And player 2, therefore, would end up with a payoff of 3, right? So clearly, 3 is better than 2. Therefore, strategy D can be stricken off from the game, and C is the sequentially rational strategy here. So player 2 would choose C, and then in the 3rd stage, player 1 would choose E, right? But next, let's come to the other decision node, the top decision node of player 2. We are still in the 2nd stage of the game, right? So what would player 2 do here? Would player 2 choose A or B? Clearly, if player 2 chooses A, player 2 gets 4, and if it chooses B, it gets only 2. So B is dominated by A. So we know if the upper node is reached for player 2 is going to end up choosing strategy A. Now the game moves to the first stage of the game, where player 1 gets to choose the game. So player 1 knows that if it chooses up, player 2 will get to play the game in the second stage at the top node and will end up choosing A. And therefore, player 1 would end up with a payoff of 1, right? And then player 1 knows that if it chooses down in the first stage, then player 2 will choose C in the second stage. And then player 1 gets to play again, and player 1 will choose E and will end up with a payoff of 3, right? So clearly, if player 1 chooses down, the end payoff, right, the final payoff that player 1 expects to get is 3. But if player 1 chooses up here in the first stage, player 1 expects to get a payoff of 1. So 3 is better than 1. So clearly, up is dominated by down. So player 1 in the first stage would choose down, and player 2 will get to play the game, and the second stage will choose C, and then player 1 gets to play the game again in the third stage, where player 1 would choose E. So this is your equilibrium path here, right, in the game. So the strategy profile that is Nash equilibrium here in this game is player 1 playing D, strategy D in the first stage, and then at the third stage, player 1 is going to play E, right? And player 2, if, game reaches the upper node of player 2, which is not the case here, but you still have to specify what would be the optimal strategy for player 2. So we know player 2 will choose A. So A, which is out of equilibrium path, but you still have to specify because that's the way strategies are written. And then player 2 at the bottom node will play C. So this is your Nash equilibrium in the game using the backward induction argument. So for every finite game with perfect information, so perfect information means, players have, they know what decision nodes they are at, right? And there is no ambiguity, meaning the two decision nodes of player 2 are not in one information set, meaning they are not connected with a dashed line here, right? If they were in a dashed line, then this is not a perfect information game because player 2 doesn't know whether he's playing at upper node or bottom node. Here we have singleton information sets, so therefore this is a perfect information game. So every finite game with perfect information has a pure strategy Nash equilibrium. This is one of the results, which can be proven, but we're not going to get into details of that here. So backward induction argument identifies an equilibrium in the case, identifies an equilibrium for every finite game with perfect information. So if there is a tie in the payoffs, right? So ties in the case of payoffs, so meaning, there is a 3 and 3 here too, over here 3 and there here 3, right? So there's a tie, right? Think like that. So if there is a tie, then there may be more than one Nash equilibrium and more than one sequentially rational strategy in the case of ties, right? But whenever you don't have any tie and game is, structured like the one I just described here in this game, then backward induction argument leads to a pure strategy Nash equilibrium of the game.